As we turn our attention to Chapter 4, we're not going to be so much concerned with how do we take derivatives and what are different derivative shortcuts, but rather what are derivatives going to be useful for. Now, in this particular section, we're going to be talking about what we call related rates. And so we have this kind of opening idea to at least kind of lay the foundation for what it is that we're talking about. And one of the most important things to recognize at the beginning of this section is that each individual question that we're going to be referencing can be kind of thought of as some sort of a moving picture. If it would have been possible for me to create a nice little short movie of something like this, I definitely would have done so. But take a look here at what we have in this opening example. Suppose that I have a conical tank, okay, so like this ice cream cone shaped sort of a tank, and water is draining slowly out of it. So you can see here that I've kind of displayed, different frames of the movie as we move from left to right. First, there's a lot of water in the tank and the puddle's pretty small, and then over time the water has slowly dripped out and the puddle's gotten much larger. So what we're going to be interested in doing is trying to understand this particular situation and how we can measure different rates or speeds of things within this particular scenario. So we'll start with noting the following. At each instant in time, the volume of the water in the tank could be given by a particular equation. Now, the nice thing about liquids is that they conform to the shape of the container that's holding them. So if my tank is in the shape of a cone, so of course is my water. So when I take a look at my water, I recognize a couple things about it. First, it has a certain depth, or we could imagine that as a height. And at the top here, there's a little circle that's going to have some sort of a radius. And so I have an R and an H that's here. Now these values of R and H are going to be used to construct a volume formula. Now you may recall, or perhaps maybe not, the volume of a cone happens to be 1/3 pi r squared times h. And that again here is going to involve this value of r and h that we see in red here in the diagram. We're not talking about the volume of the tank, we're talking about the volume of the water within the tank. So at any instant in time, if this was a movie that was playing, if I imagined I could pause the movie, right? I could pause it at a particular moment. I could easily go and measure the amount of water in the tank by just measuring these two particular things, the R, the radius of this water, and the height or the depth of the water. So the volume of the water in the tank, V, of course is changing over time. Again, if I hit play and let the movie continue to run, more water would slowly drip out of the tank, and so the value of V would constantly be changing. If I was to ever ask you, what is the value of V, I would kind of have to give you a specific time that I was interested in, because asking for what the volume is kind of too arbitrary if the volume keeps changing. So if the volume keeps changing, maybe it's changing at a particular speed, right? So if maybe I was interested in finding this rate of change of the volume, and that's represented here by a derivative, the derivative of volume with respect to time, or how quickly the volume changes over time. Anytime we see a rate of change, and kind of drew right over the middle of that, but anytime we see here a rate of change or notation like from our derivative, we can almost kind of think of that as just like, well, like a speed, right? I want to know the speed at which the volume is changing. Now, if I wanted to find this particular value, of course I could just take the above equation and I could start taking the derivative of both sides with respect to the variable of t. Now, if I imagine setting this up, this is going to look really, really awkward at first, because what I'll recognize right away is that I have no t's inside of this original formula at all, right? Time was not a variable that I needed to compute the height, to compute the volume at any specific point in time. So I just needed these values here. So what's important to note, though, again, is that V depends on time. We just stated that up above. At different times, there are different volumes. We can also kind of tell, though, that, well, the radius also depends on t then, right? Because the radius here of this top circle for the water is different in size than the radius here, and different in size than the radius there. The height also depends on the value of the time, because the height of the water is much taller at the beginning and much shorter at the end. And so what we can kind of see is that the values of v, r, and h, really all the variables here, could be thought of as having separate formulas, where we could say that I could tell you the r if you could tell me the time. I could tell you the h if you could tell me the time. I could tell you the volume if you could tell me the time. So all of these different variables here depend on time. And so what we're actually doing here then is an implicit differentiation, where all of these variables are kind of acting like y used to act back in section 3.8. That is, when I take the derivative of v, I just go, I'm not really sure how to do that because I don't know what v's formula is in terms of t's, so I'll just write that as dv dt. On this side, I could recognize the same sort of thing. Over here, I can see that what I actually have is one formula multiplied by another formula. And those formulas are both actually kind of mystery formulas. So I'll use a product rule to take their derivative. I'll do 1/3 pi r squared, leaving the blue part alone, and then I'll just do the derivative of the h. Now, since h again has a mystery formula in terms of t's, I just have to write its derivative as dh dt. If I now reverse the order, I can bring this 2 down to the front. I'll put it on top of the 1/3. And so I'm going to end up with 2/3 pi r to the first power. But remember here that r is actually a bunch of stuff with t involved. And so I'm really using a chain rule here. So I'm going to do 1/3 pi stuff squared. And so its derivative is 2/3 pi stuff to the first times the derivative of that stuff. And then I leave the h alone. So here is a crazy derivative formula that would tell me dv dt. And so you'll notice a couple things here. First off, I might be able to write this a little bit differently to clean it up. I could take out something like a 1/3 and maybe a pi and maybe even a value of an r. That would leave me with an r dh dt plus a 2 and I guess a dr dt times an h. So this is probably about as simple as I can make the derivative look. But what we'll notice is that if I was interested in computing dv dt, that is, I wanted to compute what was on the left side, if I wanted to compute this at any specific point in time, notice that there are 4 things that I would need over here to be able to compute it. I would need to know the value of r at that time. I would need to know the value of h at that time, and I would need to know dr dt and dh dt, that is, the speed at which the radius changes and the speed at which the height is changing. So what I can see is that I have a bunch of different speeds that are kind of all related together in this particular equation. And this is why we refer to these types of problems as related rates problems, because they relate a lot of different rates. So if I was interested in going ahead and actually trying to set up a problem like this to ultimately maybe say try to find dv dt, these are some of the steps that generally I could attempt to try to follow. I could go ahead and first set up an equation that relates the variables in this scenario. And to help with this, drawing pictures can really be useful. We'll see that I'll draw pictures on every one of the examples in this section. So I'll state here that drawing pictures is useful. And I'll show you how to do that again more in the examples to come. Now, after I've kind of looked at some pictures, and kind of like what we did here, I set up a formula that related all the ideas together. Here's how I would find the volume. Here's how it's related to r's and h's. Then I could go ahead and I could take the derivative of both sides. So I could say here that I would next take the derivative of the equation. Or if I had multiple, maybe equations, and I would do this with respect to the appropriate variable, which in our cases is typically going to be the variable of time. So I'll put here typically time. Okay. And then the last thing that I would do, as I can see here, is that if I have a formula for what, again, dv dt is going to be equal to, then if I could just find all of the specific values to plug in, that is, I could find a value for r, find a value for h, find a value for dr dt and dh dt, I could kind of plug in those values into my derivative and compute the value that I was actually shooting for. So that means here that I would go ahead and state that I'm going to evaluate the derivative at a specific moment in time. And again, this moment in time is typically going to be given to us in a question. Now, as I state down here, is that a common error is that oftentimes we will progress to step 3 too early. We'll start trying to plug in values into a formula before it's appropriate. And I'll try to highlight when this sort of stuff might actually happen and how we can avoid it in the videos to come.